So yeah, I'm Gilles. I will be talking to you about the Graal ecosystem and how it allows us to do Polyglot on the JVM, but actually not only. We could even remove JVM from the title. So I work for Oracle Labs in Zurich. So since I work also for Oracle, I also have to show you this. So essentially, yeah, just don't buy Oracle stock or products based on what I'm going to tell you. So with that out of the way, so very quickly, I think here I could even remove the introductory slides, but like the world is polyglot, right? There's no way around it. Like there is no single language that can do everything or that everybody wants to use. We have to embrace the fact that there are many languages and that are good for different applications, that are some people prefer one or the other. We just have to accept that. Once we've done that, like what are the challenges we need to solve, right? If we want to have all this diversity of languages. So the first problem usually is like performance, right? So you have some languages with good performance and some languages which are at least commonly known for bad performances. And that's a problem because sometimes people move away from a language just because they don't have the performance they expect. Then the other problem, which is a bit linked, is actually every language, which has been implemented independently, runs in its own box, and it's not that easy to communicate from one language to the other, right? So usually you just serialize stuff and send it over. That's costly, that's not very efficient. And lastly, like every language has its own tooling, its own way of configuring it, not only language, but even language implementations sometimes differ. And that's, if you want to be able to, in your strategy, integrate a lot of languages, it just increases the complexity of like what you have to support. So let me tell you about how we want to solve that. So what we want to do is we want to have high performance for all of the languages that we implement. So it's not like one language gets all the industry attention and gets fast and the others are left behind. We want to have the interoperability between those different languages, meaning we want to be able to call functions from one language to another, pass data without this serialization cost or without any cost actually. And then once we've done all that, then maybe we also have a good idea to simplify also maybe the tooling aspect, right? To try to have less variability in the tooling from one language to the other. So at this point you might say, well, that's good, that's already done. There's the JVM, or if you're from .NET, there's the CLR. It already does everything I've just said. Well, yeah, kind of, but actually not really. It only works on the JVM if your language looks like Java, or on the CLR if your language looks like C#. So the problem is not really solved. We wanted to have all the languages, right? Not just a small subset. That was the premise. So, and most of the problems there, the reasons why the current situation is like this on the JVM, is because there's usually a mismatch between the type system of the language you want to implement and the type system of the JVM. Or there is a type mismatch between, or a mismatch between the expressivity of the Java bytecodes and what you would like to actually do, the semantics of your language. So I think a bit more than 5 years ago now, or at least it's more than 5 years ago that we started the research on this, but we published this paper and we say, well, we want one VM to rule them all, right? Everybody wants to do that, apparently. And so, well, where are we now, right? So the solution or the approach we've taken to this problem is to say, well, the easy way for people to implement a language is to implement an abstract syntax tree interpreter. It's kind of what you would do when you learn about language implementation. It's rather simple. You don't need to know everything about compilers. It's a simple way to also debug and understand your implementation. But AST interpreters are very slow, so we need a secret weapon. And the secret weapon is like speculation, right? We provide a framework which allows you to use speculation in your implementation so that you end up with actually a high-performance implementation. So we can see here we would have some method that's been parsed into an AST over there on the left. And all the nodes are not specialized. They're just like, well, the uninitialized version of the implementation. It doesn't know like what to expect. So what does that mean? It's like the nodes can be in different states, which you can see there in the middle. So it can be uninitialized, like it has no specific specialization, but then it can be specialized, for example, to string or to double, to a certain data type, to an integer. And then during execution, right, those nodes will slowly specialize toward data types. Usually you will, on the first execution, get a very specific data type, like integer, but then while you run, you start to slowly widen the set of things that are supported just as new data comes in and mixes in. So for example, the beginning maybe integers was enough. If you have JavaScript, for example, in the beginning you'd want to represent your data as integer, but then maybe you overflow the range and then you need a real double. And then maybe someone calls your function with a string instead of an integer or a double, and you have to go to a very generic case that supports everything. So the code has been running for a while, and now we have the state we can see on the right, which is that a subtree of the graph has been specialized to only handle integers. And at this point, what we're going to do is we're going to use partial evaluation to produce good code. We're going to assume that the AST is not going to change anymore, that the specializations are not going to change anymore, and that we can compile the current code. So that means that using partial evaluation, we will produce machine code that only contains the code to handle the current specialization. So the code we will produce, we will only handle the integer case. And if we have a language like JavaScript, it's really nice if you can have to only handle integers rather than handle objects, arrays, doubles, strings, whatever. So that we'll produce very compact and fast code. It gives a chance to the compiler, essentially. But, I mean, we still have to be correct, right? I mean, it's not enough to just say, well, I compiled the version for integer, and if you get a string, too bad, it's over, I crash. No. You still need to actually support the full semantics of the language. And to do that, we use the second secret weapon, which is de-optimization, which is the ability to go from this specialized compiled code back to the interpreter, to the AST interpreter, which supports the full semantics, where no assumption has been made. So there we are free. In this world, we're free to change the nodes, maybe go to a different representation like double, run a bit more, have the time to say, well, the AST is not stable with double, and we compile that and we continue execution with slightly less performance but correctness. Okay, so the general architecture of the Graal VM. So at the base of it, there is the JVM, so the hotspot JVM, but with one special component, which is this JVM CI or JVM compiler interface, which allows us to compile code at runtime, compile native code, right? Because, I mean, on the JVM, yes, you can produce new bytecodes, but you're not supposed to be able to install native code anywhere. So this interface allows us to write a compiler in Java that will work with the hotspot VM. So that's what we did, and that's the Graal compiler. That already allows us to run any language that produces bytecodes, like Java or Scala, Kotlin, Clojure, all the JVM languages. But then we had this Truffle framework, which is what I just mentioned with the AST manipulation, and that on top of that, we can now implement more languages. So like we have Ruby, like we have heard about yesterday. We have also R, we have JS. So if we have JS, that means maybe we can do something about Node as well. So we have a Node.js implementation that uses our JavaScript implementation. And then we have another beast that we've also heard about yesterday, which is this Sulong thing, which is an interpreter for LLVM bitcode, which allows us in turn to have even more languages, meaning all the ones that are compiled to LLVM bitcode. So a quick overview of how our Node.js works. So it's basically vanilla Node.js. Everything you see here is just Node.js. Except you see the V8 part, it only says V8 API, not V8. So essentially what we did is we stripped out V8 but kept the API and then replaced that with something that ends up talking to our engine, to Graal.js. And that means we can run all the Node modules that only contain JavaScript, obviously, but also Node modules that contains a native extension that might be talking with the V8 API because they expect V8 to be under there. So, as we said earlier, one of the main goals was to get high performance. And I think it's achieved in the sense that for languages that had good implementation, we are on par, at least. And for languages which didn't have maybe very performance-oriented implementations, we gain a lot so that we can actually bring those languages into the high-performance club, which was the goal in the beginning. But then there's some question we often get is like, well, but can you actually run any useful workload on your stuff? Like, who uses this? So Twitter was kind enough to make a presentation about how they actually used and tested Graal to run some of their Java and Scala workloads. And I think they were rather happy about it. I mean, what they care about is tweet per GC cycle or tweet per CPU cycle. And in the end, tweet per GC cycle, no regression, that's already good. And tweet per CPU cycle, and I say that's already good because sometimes people are afraid of having a JIT compiler written in Java, but apparently that's not a problem for the GC. And tweet per CPU cycle, more interestingly, well, they get performance gains out of using Graal rather than the standard hotspot compilers. Okay, so the second thing that was in the Graal vision was this interoperability thing. So once we have all these languages implemented in our box, right? Now it's not in multiple boxes, it's like in one big box. Now we can start to think about making them interoperate without huge costs. And so if I had to quickly explain it, I think the main idea is that, which is nothing really new, it's just like there is a complete separation of the physical layout of data and to the logical layouts, which means that we allow the language implementers to use whichever implementation to represent the data. Like it might look like a, I don't know, JS array, which has elements from 0 to 1,000, but if there's only one element that's actually defined in this array, maybe it will not actually in memory be an array of 1,000 elements, but something maybe more compact. However, the point is that to all the other languages, it looks logically still like an array of 1,000 elements. So to maybe show you a bit more how this works out, so here we have a program which uses two languages, so some C code here and some JavaScript code over there. And the C code creates some structs for complex numbers and then passes them to an add function that has been defined by JavaScript. So there are two aspects there to high performance interoperability. So the first one is, first, the call, right? That was a JavaScript call. Like it has to be recognized that it's actually a call into C. And it's not a foreign call, right? It's not a foreign function interface. The function is not no foreign anymore. It's just a different language, but the compiler can see through it. It knows this call goes to this method, and if I want to inline it, I can. And that's very important. And the second thing is those data accesses over there, you can see the JavaScript code accesses the fields of the struct. So it's not this A and B, they are not JavaScript objects. So they are actually C structs, right? So how does the JavaScript code accesses those fields? Well, it doesn't know, but the C implementation does. So instead of trying to, I don't know, represent the data always the same so that every language can always access data, no, instead we just let the JavaScript code just ask the C code, how do you access those fields? And then we replace essentially in the AST the access to those fields with access to C fields. And now, since it's been replaced in the AST, the compiler sees through it and can optimize those accesses, and it will access the physical layout of the C struct directly in the JavaScript code. Okay, so to try to make this a little bit more concrete, I don't know if you're going to be able to read much, but the important thing is, so this is a small, as a demo, it's a small Node.js application that uses a bit of interop. So this Node.js application, you can see maybe, yeah. So it's accessing a class from the JDK, this big integer class, and doing calling some function on a bit integer and turning it into a string. We have something else that seems to be calling another unknown class, this test thing. We're going to see what it is in a second. So something that is not in the JDK, but something you defined in your application. Then we also call some R, and we create an R array and then just access an element into it. And then since it's more visual, then we also call some more R code that does some plotting and turns that into SVG. And then we run some Express app on top to run this whole. So the test class that we saw earlier, it's just a very simple hello world in Java. So if we just first install Express, right? We needed Express to run this. The interesting thing is that npm install also runs on our platform, right? So the npm was actually calling into our node implementation, and that just works. That's good. That's also already a nice test. npm is a big piece of JavaScript. We compile the Java code. That's easy. We launch this application, and then in the browser we get, well, what we expected, which is a bit of hello world from JavaScript, some code, some big integer printed out, something from Java, the test class we use, so our application, some element of the array from R, and finally the plotting from R. So now I want to talk about another aspect maybe of Polyglot, which is kind of the fact that I think you can also be polyglot within one language. So what do I mean by that? Like, if you can read this, I think if you talk to someone who programs Java and who is used to use, I don't know, Java 6 or 7, like some people are locked into those versions for whatever reason, they will tell you this is not Java. First, I see Lambda expressions, that's not in Java 6, that's not in my Java, and this stream API, I don't recognize it either. By that I mean that even within a language, languages evolve, right? And sometimes the version from the past and the version from now don't look alike at all. It's almost like using different languages. And that has consequences as well. And again, if I put that into our vision, it means, well, we think Java 6 should run fast, but Java 8 should also run fast in all its different programming flavors. So what I did here is a small application which uses the Stream API to do stuff. It just does some filtering, does some mapping, some more filtering, then averages or sums So it's a very badly written benchmarks, but at least it does warm up and the basics. And we just call this a lot of times. So let's just compile it and run it on a standard hotspot JVM. So it's okay. I mean, it's like 460 milliseconds per iteration. That's okay. It starts up rather fast. The difference between the first iteration and the next ones are okay. So let's see what happens when we run it on our VM, right? So the startup is not that great. But in the end, the performance, once it's warm, is great, I think. It's 130 milliseconds, which is a big improvement. And I think that that's a polyglot aspect because the compilers in Hotspot are very good. Don't get me wrong. But they were maybe not made for the kind of programs we see in Java 8. And we think those programs should also be fast, not just the old Java code. So there's something I wanted to show you. Like the first step, we just compiled this Java file, right? And I just ran the command, but actually if we time it, we see, well, it's like half a second and about 2 CPUs are being used. It's okay, people are used to compilers being slow, but I mean, it's a small Java file, right? Half a second. It's the same problem basically as in the second example. If the more Java you run, I mean, our compiler is written in Java, so we run a lot of Java, and we have this startup issue. And so we think you should be able to run all languages fast, so that's one good thing, but what do I mean by fast? Obviously we mean peak performance usually, but I think startup also matters in some use cases. Well, it's limited, but there are use cases where you care about startup. So yeah, if we run it few more times, it really seems to be half a second per call. It's not just the file system being called or something. So what I'm showing now is our solution to this problem. And what is it? Well, it's something we call Substrate VM, which essentially is like a very reduced JVM. We cannot call it JVM actually. That's why we call it Substrate VM, because it doesn't support class loading at runtime, and that's kind of the basis of Java. But for many use cases, you don't really care about loading classes at runtime. You just care about running an existing application and running it fast. So what I'm doing here is I'm creating an image out of the Java-C compiler. And now I'm going to compile the same Java code using the compiled image. And now we see that's about well, that's very fast. That's 10 times faster, I think. It was half a second. Now it's 0.5 second. So it is possible to get fast startup also on our platform thanks to this, thanks to SVM, which precompiles things. And there's another way to look at it. So this image is just an ELF file or whatever binary is on your platform that we can run directly, and there's no JVM, there's no startup cost involved anymore. So the other thing is, well, what about this Node thing, right? Is it really fast? So if I write a hello world in Node, how fast does it start up? That's what we saw in the previous talks, right? Like people write simple pieces of Ruby, then run it and complain that it's not fast on the first iteration. That's the same here for this Node.js thing, which is just a hello world. And it prints hello in, I think, 2 seconds, right? Yeah, 2 seconds. That's not terribly fast. And so we can apply the same thing, which is instead of our Node implementation can either use a JVM or actually can use a pre-compiled version of our Graal.js interpreter. And that helps us a lot because now the same hello world runs in, let's say, the slowest one seems to be 140 milliseconds, which is much faster than 2 seconds earlier. So we also think that startup is important, and that's why that's one of the reasons why we extend the original vision to say, well, it's high performance, but also we want to be able to produce native compiled code, both for startup, but for another very important reason, which is embeddability, right? Embeddability in the JVM was already a given since we run our whole platform on top of the JVM, but embeddability into native applications, which might have different requirements and different expectations, is also very important. And thanks to what I just showed you before, this Substrate VM ID, which allows us to compile ahead of time and get rid of this startup cost, helps us achieve. So the whole everything I've been talking to you about is available online. You can download the whole Graal VM package that contains all the languages I've been talking about, the Graal compiler, the language implementations, etc. on this OTN webpage. I think if you look for OTN Graal, you'll find it. A lot of our source code is open source on GitHub. So there's this Graal VM project on GitHub where we have most of our source code. By most, I mean the JIT compiler, Graal, the Ruby implementation, and the R implementation. And lastly, there's a bit more open source code as well on OpenJDK, but that's more about the hotspot VM and the JVM CI layer I talked about earlier. That's might also make you a bit suspicious because but essentially I'm saying we need modifications in the source code of the JVM to get our stuff to run. That's not very nice. Maybe you don't want to use a different build of the JDK just to run this. Well, good news. JVM CI, this interface that we built for our stack, actually is going to be in there starting from JDK 9. So you will not need a custom JVM anymore to run our stack. That's it. So thank you for listening, and if you have any questions.